this interim test. Yes. Okay, so let's take a look at that right now, as a matter of fact. Okay, so let's take a look at why we're doing all this. Okay, I'm going to look away from the comments for now because I'll never get started if I don't. Okay, so at any rate. Okay, so why are we doing all this? The reason why we're doing this is that we often want to compare two groups. Okay, I'm calling them Group A and Group B. Group A and Group B, they could represent Group B. They could represent a ton of things, right? Group A could be a group that took a experimental drug. Group B could be a control group, which got a placebo. They didn't take the drug, right? I mean, we might want to know what's the average blood pressure for Group A. Is it different than the average blood pressure for Group B, right? I'll put a little A down here and a little B down here. We're interested, is there a difference between these two groups? Okay, and usually we're interested in not just the sample that we take for these groups, we're interested in the entire population that this represents. Maybe the target population is men over 60 years old, right? So blood pressure treatment maybe is something that the drug company wants to market to men over 60 years old. If they knew the true average for blood pressure for if you didn't take the drug, if they knew what mu was, and mu for Group B would be, like if you didn't take the drug, and what the mu for every man over 60 that might take this, mu for Group A, if they knew what those were, they would know if they're different or the same. There's no need to do a study if they actually knew what the average was for the entire population if you gave everybody the drug versus if you didn't give nobody the drug. If they knew what that result would be, there would be no need for a study. Okay, so since you almost never know that, and your only clue is to take a random sample of people from this population and divide them up into two groups, either naturally or artificially, in this case artificially, randomly divide them up into two groups, give the drug to one group, give the a placebo to a second group. Maybe you'll take 30 people and give them the drug, and yes, oh, I got a problem behind me. Yep. Yeah, why does that appear? It seems to appear randomly, right? Let me get this out of the way too.
Sorry, what did you write about n equals
30? I said, let's say I just picked a number out. I said, let's say that the drug company wanted to test this drug. So they gave the drug to 30 people in this randomly selected men in this age group. And they gave a placebo to 30 randomly selected men in this group, right? They just picked 30 out. We just went through a lecture where we talked about power and sample size and so on and so forth. They might actually choose that sample size based on what their guess is on the sample size, what their calculation, I shouldn't say guess, what their calculation might be on what they think that they would need in sample size to prove this, right? But let's say they took 30, they decided they need 30 people. Well, now when you give the drug to 30 people, you're going to get an average X bar for that sample that you take, right? X bar, you're saying, hey, 30 is a pretty big sample. X bar is probably pretty close to what the mean if I had given this to all men in that age group. And then you get X bar, that's for Group A. Then you get X bar for Group B. Okay. So now the problem here is that now you don't really know what the population mean, and what the of these two groups is. You only know what the sample mean is that you took. And now you have to use that to deduce whether these means are equal or if there's a difference and the drug does help these men, right? So you have to deduce that. The problem is that this isn't necessarily mu, right? It might be close to mu, it might not be close to mu. However, you have a tool, and that tool that you have is called the confidence interval. That's the first tool in your arsenal, is the confidence interval. You can determine that If I got this mean and I took these 30 people and I knew, well, blood pressure was 110 and 109 and 115, and you could calculate a standard deviation and so on and so forth. You could calculate a standard error by putting over square root of the sample size. And you could determine that this may be the mean I got from my sample, but I'm 95% sure that my population mean, this mu that I don't know, is between this number and this number. I'm 95% sure it's somewhere in this range, right? So now this other population, I don't know that I got the mean for that population, people that don't take the drug. I don't know if I got that right either. So I have another confidence interval for this group over here. I'm 95% sure the real mean for this group is between these two numbers. Okay? Well, if this number on this side is going to be 90 to 110, we're 95% certain that the true mean is between 90 and 110 for people who take the drug. And for people who don't take the drug, it's between 120 and 140. Well, that's a pretty clear situation, isn't it? This drug works, right? With a high level of confidence, this drug works because we're 95% sure that if you don't take the drug, you're going to be in this range, the mean for this entire population. But if you do take the drug, you're going to be in this range. We're 95% sure of that also. So that's a pretty high level of certainty. Problem is that never happens. What happens is we're going to have some overlap here. And we have to determine what's the probability. If this had been 110, let's say this was 105 to 125, right? There's a bit of overlap between these two. In other words, there's a chance we could have gotten a value here that was here and a value here that was way down here and actually lower than the value that we got for this side. So it actually looks like it's the opposite relationship than what it really is in real life, right? Things could get very messy. So we need a way of figuring out what's the probability that I can start off by saying these two means are equal, but have enough confidence in the difference between these two means to be able to say, oh, I'm 95% sure they're not equal. Okay, 95% confident. Okay, another way of saying that is that I have an alpha error of 0.05 or less. Right? In other words, I think there's less than a 5% chance that I will make this assumption, reject the null hypothesis that these two groups are equal, and only make an error less than 5% at a time. Make that kind of error if I'm wrong, and they really are equal. Okay, that's really what we're doing here. Okay, and there's a lot of situations where we might wind up doing this. Let me give you a couple of situations where we might be interested in doing this. Okay, let's see. Okay, one situation is I'm going to say, let's say, I know that the mean SAT score for Brooklyn College, okay, mean SAT scores for Brooklyn College. We actually surveyed, we went and we got the records, and we know that the true mean SAT scores for Brooklyn College is equal to, what's a decent SAT score now, about 1,800? Or is that high? That's high, right? I don't know. What's that?
I don't know the newspaper.
Yeah, they changed it now. It's so different, right? I'm going to say 1,600, right? We know that for a fact. We know mu, right? However, now I go over to Hunter, and I don't know them. They weren't recorded. Maybe they didn't require, maybe Hunter didn't require people report their SAT scores or something like that. Who knows? Maybe they have different admissions procedure, right? So we don't know what the scores are for Hunter, right? So we're going to sample. The only way we can find out if we don't know what the mean for Hunter is, right? The only way we can estimate it without actually taking every Hunter student and asking their SAT scores is to take a sample, right? So I'm going to take a sample of size 100. I'm going to sample 100 students, right? Okay, so now I sample that group of 100 students, and I say to myself, oh, the mean, what do you think guys think? 100 students higher or lower than Brooklyn College? Okay. We say that the mean that we find for that sample of 100 students, notice I use X bar now, is equal to 1,700, right? Okay, so now the problem now is that, well, it looks to me like the mean for Hunter students is higher than the mean for students from Brooklyn College. Problem is X bar may not be the same as what mu really is, right? If I took a sample again, it might come out to 1,500. If I took a sample again, it might come out to 1,650, right? The variability of the sample tells us something about that, what the probability of that occurring is, right? So one way that I could do this is I could say, there's no way for me to know for sure what the mean is for Hunter students. Let me make sure these guys online can hear me. You guys still okay? It's out of 2,400. Okay, I see. I should have gone online to find out these answers. Okay, just want to make sure you guys can still hear me. Okay, so the 1,600 is mu, right? Because that was given. In other words, at Brooklyn College, they actually required everybody to report their SAT scores. Okay. But at Hunter, they didn't. So we're going to randomly sample 100 Hunter students. That's why you don't see N over here, because N over here is everybody, right? They actually know the true mean for the population at Brooklyn College. But at Hunter, we don't know the true mean for Hunter students. We only know the average for our sample, a random sample of Hunter students. Okay, so now I need to quantify how well I know that. And the way I do that is, one way is to calculate a confidence interval. Okay, so I'm going to calculate a confidence interval for this. There's a couple of ways I can do this. One is, since we know the entire mean for Brooklyn College, I may know that the standard deviation is 100. Perhaps I know that from Brooklyn College because they sampled every student and actually can calculate the standard deviation. Well, I could use that sigma and say, I got no reason to believe the variability is, even if the score is different, maybe the variability is the same. So I might want to use to calculate my confidence interval. I might want to say that I'm going to use the sigma, the true population standard deviation for Brooklyn College. Assume it's the same. So there's one situation. Sigma is known. If sigma is known, in order to develop a confidence interval for this 1,700, my X bar, what do I need to know? Standard error. I need to know the standard error. And I calculate that by taking sigma over the square root of the sample size. So standard error is going to be equal to sigma, which is 100, over the square root of sample size, which is 100, which is 10. So the standard error is equal to 10, right? Now, let's say I don't know that, or I don't want to assume that. Where's the only other place I can find an estimate of sigma here? Well, I took a sample of 100 people. I could take the standard deviation for this 100 people. Let's say it's equal to 200. Standard deviation for these 200 people, and I could assume that approximates what sigma is for the population. From the 100 people. In other words, I actually calculated from the 100 scores. Okay, like in other words, just like we did in the beginning of the semester, just like you would calculate the mean just by adding them up and dividing by 100, I take the standard deviation. Maybe I use Excel or something like that. But I actually calculate it, right? It's better to know sigma, right? But we learned kind of a general rule that we decided on. And that was that if the sample size is greater than 30, we'll ignore the fact that we don't know what sigma is, and we'll allow ourselves to use standard deviation instead. Okay, so I could have done it either way. Okay, so I could have used 200, I could have used 100 from this study, and so on. So this would have been, standard error here would have been equal to 200 over 10, the square root of the sample size. So it might have been 20, let's say, whatever it came out to be. It doesn't matter. Okay, so I'm gonna go with the first one, just so that we can work on this. Okay, so now I gotta calculate my confidence interval. My confidence interval is equal to my point estimate. Okay, what's my point estimate? It's my proportion It's my mean that I calculated. It's whatever. It's where the middle is. My point estimate plus or minus, okay, and the z-score for, since we're generally going to use alpha is equal to 0.05, and since I don't know whether Hunter students had higher scores or lower scores, I'm going to use a two-tailed test. I'm going to put over here z for alpha over 2, right, times the standard error. Okay, and what is that equal to? It's equal to 1700. I'm going to redraw it. X bar plus or minus. What is my z-score going to be for 0.05 two-sided? It's going to be 1.96 times my standard error. What's my standard error? 10. Okay, so X bar, so it's going to be 1700 plus or minus 1.96, so 19.6. 1.96 times 10. So our confidence interval is going to be 150.4 to 199.6. That's that right? I think it's pretty right. Okay, if I'm wrong, don't worry about it. So let's see. I'm sorry, 1700. It's if it should have been 1700, I guess, right? So this is going to be 16. I'm going to round it off here. 1680 to 1720. I'm sorry. That's 1680 to 1720. That's right. Okay, 1680 to 1720. So now I'm 95% sure the true mean for Hunter is between 1680 and 1720. And what do we know Brooklyn to be? 1600, right? So here we are between 1680 and 1720 for Hunter, and here is the scores for Brooklyn College down here at 1600. If I set up my null hypothesis that the mean for Hunter is equal to the mean for Brooklyn College, do I reject that null hypothesis?
Yes.
Yeah, I reject it, right? Not true. I'm going to reject it. I'm going to accept the alternative that they're different. I can kind of use the t-test this way. Is this really the way we do it, though? I mean, you can see how you might be tempted to use it this way. Well, in reality, we kind of use it a bit differently. We do what's called a single sample t-test. I'm going to do exactly the same thing, except I'm going to do it in the form of a t-test.
I have a question.
Sure.
You said that in 10 was the last example.
Yes.
I'm not sure what you said, if it was the standard deviation or the standard error.
If the sample size is greater than 30, right, I allow myself to use that standard deviation as if it were the population standard deviation, as if I knew sigma, even though it's only S, the standard deviation for the sample. I'm letting myself use that. Not important yet. It's about to get very important pretty soon, okay? Because we're going to get into this idea of T. So now, instead of using the confidence interval in this manner, I'm going to actually kind of phrase this another way. First, I'm going to start with the same null hypothesis: is that mu for Hunter is equal to mu for Brooklyn College. Okay, so now my alternative hypothesis is that they're not equal. Again, it's a two-sided test. Almost always we're going to deal with two-sided tests. When we get towards the end of the semester, as we get a little further on, maybe next week a little bit, we'll talk a little bit more about single-sided tests, just so you recognize them and know how to react to them if you have to wind up dealing with one or calculating for one, and so on. So now this time I'm going to look at this a little bit differently. X bar for Hunter was equal to 1700. Mu for Brooklyn College was equal to, we know that's 1600, right? So instead of looking at it as a confidence interval and a number, and whether that number is outside of that confidence interval or not, I'm going to look at it differently. I'm going to say to myself, how many standard deviations apart standard errors apart are these two values. How do I calculate the number of standard deviations apart? Well, I say the z-score difference, the number of standard deviations apart, is equal to x bar minus mu over the standard error, right? That'll give me how many standard errors apart they are. And if they turn out, if z turns out to be greater than 1.96 standard errors, I can say that they're different enough that I can reject the null hypothesis. Okay, let's see how that's going to work. Z, I'm going to use for standard error, I'm going to use say it's known or that we calculated it from SD because the sample size was 100. Standard error is equal to 100 divided by square root of 100. 10 is equal to 10. So now I'm going to calculate this. Z is equal to 1700 minus 1600 over the standard error, which is 10. I'm gonna change this up a little bit to make it come out a little bit more reasonably. I'm gonna say that the standard deviation is equal to let me see, what can I do here to make this a little bit more reasonable? 100. I'm gonna say 300. Okay, it comes out to 30. Standard error comes out to 30. Okay, so what is this going to be equal to? It's going to be equal to 1700 minus 1600, which is there's a 100 difference, divided by the standard error is 30. So it's now remember, it's x bar is 1700, so it comes out to be plus 3. My z-score, these are 3 standard deviations apart. I know right away that I can reject the null hypothesis because I only have to be 1.96 standard deviations apart to reject the null hypothesis. But you want to know something? Look at this. This is pretty interesting now. If I take a normal distribution, z distribution, and I draw it, I'm going to draw it on the next page. I happen to have something here. And I look for what's the probability that I would get something that's 3 standard deviations or more apart. How likely is it that I would get something that far up on this distribution? Okay, well, if I go to the z table and I look up what the probability of getting something that has a z-score greater than 3 or greater, what do we get? 99 point, is it 99.1? No, well, it's 99.1% to the left, right? 0.991 to the left, but this is only 0.008. I'll take your word to 0.009. I'll take your word for the percentage. It sounds about right. 99 point. Well, that's if you use the. That's if you use the. That's if you use the estimate that we were using. If you actually look it up on the table, what does it come out to be? Anybody know? You got it on the table there. I think it's worth looking up. Agresti.
1.3.
Yeah, T.
Yeah, 0.9987.
0.998. Whoops. 0.998. Okay, 0.999. Okay, so that leaves 0.01. Okay, so now, remember in the beginning we said we didn't know whether Hunter is going to be on this side or on this side. So we actually have to double that percentage because it could have just as easily been on this side. So it could be that the probability of getting a result from this population, from the population of means of 1600, which, in other words, if we took a sample of size 100 from Brooklyn College, when we know the mean is 1600 and sigma is equal to 30, in our or 300 in our estimation, if I took that, the probability I would get a value as high as 1700 is 0.001. That's 1700. There's 3 standard deviations, 1700. Okay, so the probability that I would get that extreme, 3 standard deviations away on the low side and high side, is 2 times this probability of 0.002. I know that they're itching to tell me stuff online, so I'm going to take a look in a second. So this is our p-value. That's the probability we would be saying these are 2 different groups if, in fact, they were all part of the Brooklyn College group. They were the same as Brooklyn College. Okay, that's the probability that this would occur. Okay, so what do? We calculated z, and we decided, well, if it's greater than 1.96, we're going to reject the null hypothesis. That's the critical value that I will use, because 1.96 would represent 2.5% here, 2.5% chance of being wrong here, right? Being part of the Brooklyn population, being the same as Brooklyn and getting this result, right? So that would be alpha is equal to 0.05, two-sided, 2.5% here, 2.5% here. Well, in this case, what I need is that I have to show that P is less than alpha. Okay, in fact, P is very small compared to alpha, which is 0.05. So the probability of my being wrong, if I reject the null hypothesis and say these aren't the same, is way less than my tolerable level of error that I'm willing to accept. Okay, so now I'm going to do this one more time. Let me see what's going on online. Okay, can you write the formulas for the problem? Yeah, we're going to get to that in a second. I'm going to show you a whole bunch of formulas for this. So it'll make it a lot more automatic for you. You won't have to think this out every time you do it, hopefully. Okay, so now I have another situation though. And that situation is, what if my sample size, here's Brooklyn College, mu for Hunter is equal to mu for Brooklyn College. That's my null hypothesis. My alternative hypothesis, again, that they're not equal. Hunter, not equal to mu for Brooklyn College. Okay, again, so now this time I'm going to say my sample size is equal to 25. Right? And I'm going to say that, I don't know sigma. Right? I don't know sigma for the Hunter students. So I have to calculate my standard deviation from these puny little sample of size 25, less than 30. And it comes out to be, say, 300. Okay. Well, I'm going to say, let's say it comes out to be 400. Okay? I got a reason for this. Trust me on this. Okay. So actually, I'm going to even go a little bit further. No, I think 400 is enough. Let's see what happens with 400. Okay, so now when I calculate my standard error, the only thing I can base it on is S, right? The standard deviation for my sample, which is 400, over the square root of my sample size, which is 5 now, right? So what does this come? That comes out to 80, right? My standard error is equal to 80. Okay? So now I have to say to myself, okay. So now I say to myself, well, are these two means? Is that mean of X bar? Again was 1700 for Hunter, and mu was 1600. Remember, it's known for Brooklyn College, right? This is called a single sample test, right? Because we know the result for one side, the mean for one side, but the other side is based on the sample. So let's calculate what our z-score is this time. I got a problem though. I can only use the z-score if I know the population standard deviation sigma, or if my sample size is large, certainly greater than 30. That's not the case here. So instead of using z, what do I have to use? I have to use t, hence t-test, right? T-distribution. There's a different t, I'm sorry. Sample, when we don't know the population standard deviation, sigma, and when the sample size is less than 30. Okay, so now we got to calculate t instead of z, right? So now here's t. We want to know how many standard errors apart for t is. Okay, how do we calculate that? Well, again, it's x bar minus mu over the standard error. So what is t equal to? It's equal to 1700 minus 1600, which is 100, over the standard error, which is 80. So t is equal to 1.25. In other words, these are 1.2 standard errors apart. Can I reject the null hypothesis? What do you think? No, because it's less than 1.96. I'm going to manipulate these numbers a little bit. I'm going to say that this was 200 instead of 400, and this comes out to be 40, right? So this is 40 down here. So now this is 2.5. the number of standard errors apart. Can I reject the null hypothesis now? Yeah, because it's more than, hang on a second. It's more than 1.96, but we can't use the z distribution now because the sample size is small. We have to use the critical value that we need of t to exceed to reject the null hypothesis. Let's pull up the t table and take a look at it. Okay, so let's go to t table. Okay, it's on Blackboard, I think. Where is it? T table, like Rusty. Hopefully it'll come up easily and I won't have to search too much. Oh no, here it is. There it is. I got it. What's that? Oh, it doesn't matter. It's a t-test. Okay, we know that the t-value for the difference between the mean and the x bar is 2.5. So now let's see how big t has to be to give us less than 5% chance of being wrong if we reject the null hypothesis. Okay, so we want our chances of being wrong to be less than 5%, 2.5% in each tail, two-tail test. So which of these columns gives us 2.5% in each tail? What's this middle one over here? And conveniently, they point out that's a 95% confidence interval. But we're interested in this middle column. If we were interested in an alpha of 1%, we would be using this 0.5% in each tail, or 99% confidence. So we're interested in this middle column. Now notice that if we had a sample, how do we calculate degrees of freedom? It's a sample size minus 1. So if we had a sample size of 5, then our degrees of freedom is 4. What is our critical value of t that we need to exceed? 2.7. Would we be able to reject the null hypothesis with 2.5? No, because we didn't exceed 2.7. If we had t is equal to 2.5, we didn't exceed it. If the sample size were 7, would we be able to reject the null hypothesis? 2.36. Yes, we could reject the null hypothesis. Of course, when we calculated our t-value for the difference between the two means, it came out to be 2.5. Since our critical value of t that we need to exceed, see these are critical values, the number that we need to exceed to have less than 5% chance of being wrong if we reject the null hypothesis, in that case it's 2.3 or so. So we did exceed it, was 2.5. So the distance between these two numbers is big enough, bigger than in standard errors, bigger than the critical value of t. So we can reject the null. In fact, for our sample where we said 25, sample size 25, we only have to reject 2.06. Now, if you notice what happens here as the sample size goes up, what happens to the critical value of t? It gets closer and closer and closer to what value? 1.96, the same as the z-score, right? So what we do is we arbitrarily say, if the sample size is bigger than 30, it's so close to 1.96, we'll just use 1.96. Okay, generally, that's kind of what we do. Legitimately, you don't necessarily have to do that. You could actually calculate it, exactly. In fact, when you use software to do it, it actually calculates it exactly. So now, what does this do for us now? Well, what this does now is that we know, for instance, we just found the t-score was 2.5, right? Well, if I go across here at a sample size of 24, right, degrees of freedom 24, I can still reject the null hypothesis for this column. What's this column? This column is 98%, or an alpha of 0.02, right? But I can't reject the null hypothesis for the next column, 2.8, which would be a 1% alpha. So I know my p-value is somewhere between 1 and 2%, right? That's the real chance of me being wrong if I reject the null hypothesis. This is kind of a clunky way of kind of like, calibrating this chance of being wrong. If you use SPSS or the other software, you can actually calculate a real p-value to see what the real probability is, not just whether it's less than 5%, but what the actual probability of being wrong is. In other words, p is equal to, in our case, say 0.015. something like that. Okay, which is nice because then you can put that into a paper and not just say, the probability of our being wrong is less than 5%. You could actually say the actual probability of our being wrong if we reject the null hypothesis is 0.01 or 0.019 or whatever it happens to be when you calculate it. We're actually going to give that a try in just a little while. Okay, so are you guys okay online with this so far? Are you catching on to this? Okay, because I want to move on to this, and I actually want to do a couple of quick examples of this. Of course, yes.
So when you calculated t-square equal to 1.25, you said we could not reject the null.
No, because they were only 1.25 standard deviations apart. The numbers, the x bar and mu were not far enough apart for us to say that the means of those two populations are different. Right? They have to be at least one. If we have a large sample, at least almost 2 standard deviations, 1.9 standard deviations. In this case, with a sample size of 25, they have to be 2.06 standard deviations apart. They have to exceed that critical value of t that we need to say they're far enough apart. And how do you calculate t? You subtract the sample mean from the population mean for a single sample test, divide by the standard error, because it'll give you the number of standard deviations, standard errors in the case of a sample. Okay, so now these examples come from a document called Lab Exercise June 29th, which is on Blackboard. I'm not going to go open up the document right now because I actually have them open right here. Okay, so now here is a sample of size 9, right? Okay, so if I tell you that the standard deviation is of this population, sigma, I'm going to rewrite that as sigma. If I tell you that sigma is equal to 3, right, we're going to calculate a confidence interval. Okay, so what's the average here? Okay, and these are just in fact, they're a silly set of numbers, really. Okay, the average is 9.9 approximately. Okay, so what's my confidence interval going to be? Well, in order, this is x bar, right? I need to know what the standard error is in order to calculate my confidence interval. So what am I going to use for the confidence interval? Well, sigma is equal to 3. I know the population standard deviation for this population. Kind of an unrealistic situation, but we know it's 3. So how do I calculate that? It's equal to the square root, it's equal to sigma, which is 3, divided by the square root of the sample size. Sample size is 9, so I'm just going to put a 3 down here. So it's equal to 1. Standard error is equal to 1. So what is my confidence interval going to be? My confidence interval is going to be equal to x bar minus 1.96. Now, how do I get away with using 1.96 instead of the t-value here? Because we know sigma, we know the population standard deviation, right? So it's going to be equal to 1.96 times 1, right? So it's going to be 7.92. And on the other end, if I add it, it's going to be 9.88 plus 1.96 times my standard error is going to be, so my 95% confidence interval is going to be 7.9 to 11.4. I'm 95% sure that the true population mean is between these two numbers. Well, let's say I came along and said, the mean mu for population number 2 is equal to 12. Can I say that population number 2 is, can I reject the null hypothesis that population number 1, my sample, where my sample was drawn from, is different than population number 2? I'm going to do a t-test, okay, a single sample t-test. So t is going to be equal to x bar, right? Whoops. I'm sorry, actually t, I don't use t, do I? Since I know sigma, I use z. Z is going to be equal to the X bar minus the mean of the population divided by the standard error, which is 3, right? 3. I'm sorry, 1. You're right, 1. Okay, so I'm going to put this in parentheses. Okay, hit enter. And what is my z-score? My z-score happens to be negative because it's my sample was to the left of my mean. So it's minus 2.1. So what number does it have to exceed, that z-score, in order for me to know that the p-value is less than 0.05? 1.96, because we're dealing with z. Great. That's all I need to know about this. I'm done. I did. Basically, this is a single sample t-test, except we use z because we knew population standard deviation. 99.9% of the time, you're not going to know the population. You're going to be faced with this situation.
We can reject the number.
Oh, the first one we reject, right? Because it's bigger than 1.96. Because we're using z, right? Yeah, it's big. Yeah, remember, it could be on either side. Could be it's that far away. Just happens it's that far away to the left than to the right. So it happens to be a negative number. So minus 2.11 is more than 1.96 standard deviations away from the mean. Okay, got it? Just because it's negative doesn't mean that it's any closer. Okay, so now let's take a look at the situation where we don't know the population standard deviation. We have a small sample. Yes?
If the mu had been 13, we just know visually that it's outside of that interval. Do we have to?
If mu would have been 13, well,
mu would have been 13.
Yeah, well, I don't know. Maybe your vision is better than mine, but I don't know if I would. Because it's 1. I guess it's pretty easy to see the standard error.
Yeah.
Because it happens to be 1, it's pretty easy to see. It's not always going to be exactly 1, right? We got lucky on that. In fact, you want to know something? It's probably not even.
We should do the z-score.
Yeah, you should do the calculation. In fact, what's going to happen in real life? This is what you're going to be faced with. You don't notice that the standard deviation no more than you know X bar, right? You don't know what it is, right? We're taking it. What's our confidence interval? We took a sample of size 9 from this population. What's our 95% confidence interval? Okay, so what's the average equal to? The average is going to be the same as before, right? These are the same numbers. Okay, average is that, right? Same as before. What's our standard deviation going to be equal to? Let's see what the standard deviation of this is. It's 2.93, a little less than 3. I was pretty close at 3, right? Okay, so now, let's see. Now I got to calculate. So the only estimate I have, the only way I can guess what the population standard deviation is, what sigma is. The only evidence I have of what sigma is this 2.93. I have no other way to figure it out, right? So if I want to calculate a 95% confidence interval, I do the same thing I did before. Okay, now 95% is going to be equal to X bar, right? Minus, now do I use 1.96?
No.
I got to use the proper t-score for this. It's a sample size of 9, so I look up the t-score for an alpha of 0.05 for, right?
8 degrees of freedom.
For 8 degrees of freedom, exactly. Because sample size is 9, right? Okay, so let me, Gresty. I want to pull it up so everybody can see it. Okay, here it is. So for sample size, degrees of freedom equals 8. My t-score for 5%, remember one tail is 2.5, the other tail 2.5, so that's 5%. You can also look up here to confirm it. Okay, is 2.3. So instead of using 1.96, I say 2.3 times my standard standard error. I forgot to calculate my standard error, didn't I? Hang on a second. Okay, it's equal. The standard error is equal to. The standard error is equal to sigma divided by the square root of the sample size, which is 3.
So for standard error, we can assume that sigma is standard deviation.
For a small sample size, right? For a small sample size, our only idea of what the population standard deviation is is the actual standard deviation of the numbers in the sample. Just like the mean approximates the population mean, the standard deviation for these 9 numbers approximates the population standard deviation. But we're about to get burned, right? Because the piper has to be paid for this inaccuracy using population standard deviation in sample standard deviation instead of population standard deviation. And the place where we pay the piper is when we calculate the confidence interval. So the confidence interval is going to be equal to the mean plus, I'm going to do minus first, minus, right? Not 1.96, but we said 2.3 for a t-score for 9 degrees, for 8 degrees of freedom, times my estimate of the standard error, which is, instead of 1, it's 0.97 this time. Okay, and what does that come out to be? Okay, comes out to be 7.63. Okay, and our upper end is going to be equal to, it's going to be equal to our mean plus 2.3 times our standard error. Okay, hit enter. Oops, I did something wrong again. No, don't hound me. Excuse me. You know what it is? Wrong notation. Okay, there we go. I think that'll work now. Yeah, it's okay. Yeah, it doesn't matter. That part I didn't have to worry about. I was doing it as if I was writing a formula in the Texas Instrument calculator. So at any rate, so our confidence interval is 7.6 to 12.1. Now, if I went back and looked here, when I knew the population standard deviation, it was 7.9 to 11.8. It was closer. It was narrower range. We had more certainty there because we knew what sigma was, and we could use 1.96 instead of 2.3. Okay, so now if I go back to this, right? So I got my range here and so on and so forth. If I looked at this as if we were doing a t-test, right? What would this look like instead? What's the value of t? We're not going to use z this time. We're going to use t. The value of t is going to be equal to the mean, which was this, minus, what did I say I was comparing it to? I was comparing it to 12, right? Before, divided by my standard error. Okay, and what's the big difference here? The big difference here is that I'm doing the same calculation as I did before. 9.88 divided by minus 12 divided by the standard error. It's going to come out pretty much the same number. The problem here is that in order to reject the null hypothesis, what does the value of t have to be? Well, now again, I got to go back to my t table. Right? What does the value of my t table t have to be in order to reject the null hypothesis for 8 degrees of freedom? It has to be 2.3. Right? Can I reject the null hypothesis here? No, I can't, because t is smaller than 2.3. I haven't exceeded the critical value of t. Right? Pretty good. That's all there is to this. Right? You kind of the same kind of thing you're doing to calculate the confidence interval, you're doing to calculate the value of t or z, as it may be, depending on the sample size or whether you know the population standard deviation. Okay, so now